Okay, so we've talked a little bit about what basic magnetic resonance is, and we've talked about how we can localize the signal in MRI using 2D Fourier transform imaging. Now I'd like to talk about how we get contrast so that we see why it is that we see different signal intensities with different tissues with the different pulse sequences. So I'll go through the stuff that you all know. One is T1 weighting. Let me think. Michael, what is T1? What is a T1 weighted image?
A T1 weighted image is a sequence where the TE is short. You have a short TE, and it's an image that has kind of bright fat on it.
Okay, that's good. Now, the basic definition of a T1 weighted image is an image where the signal intensity on the image is predominantly determined by the T1 relaxation tissue of the tissues. And the way we get that with standard spin echo imaging is using a short TR and a short TE. And we'll try to explain why that's the case as we go forward. Okay, so going back to the first lectures we had, Yuri, what is T1?
T1 is the amount of time it takes for the hydrogen for the protons to get back to their original to the to their baseline level after excitation. Or I'm sorry, it's 63. It's 2/3 of time it takes to get to the baseline after 90-degree pulse.
Okay, so after the 90-degree pulse, what happens is the bulk magnetization rotates into the XY plane and the Z component goes to 0. And T1 is basically the time it takes for the signal to recover one standard deviation after it goes to 0. And that's about 62% or about 2/3, just like you said, of rise up along the Z axis. And that's really the Z component of the bulk magnetization vector, the component in the direction of the magnetic field. Good. So, and now, Sean, what is T2?
It's the time it takes for, again, like 62% or one standard deviation of the signal to to disperse in the XY plane. So that would be the XY signal.
Okay, so the spins to disperse, or it's a time
decay.
Yeah, one standard deviation of the decay of the XY component, which is about the time it takes for the XY component to go down to 1/3 of its maximum value. And we know from before that the XY component drops much more rapidly in biologic tissues than the Z component rises. So the T2 time is roughly in the range of 30 to 60 milliseconds. The T1 time is generally up in hundreds of milliseconds. Okay. So another way to look at this on a graph is if we look at the Z component of the bulk magnetization vector, after the 90-degree pulse, it drops down to 0, and then it rises exponentially back up to the baseline value. And then after a TR time period, we give another 90-degree pulse, and it drops again, and then it rises back up again. And if you have a T1 of 200 milliseconds, that means it rises very rapidly. If you have a T1 of 400 milliseconds, that means it rises more slowly. Now, looking at a curve like this, Sheila, and this is time in seconds down here, at what point in time, if we got an image, would you expect the signal intensity between these two tissues to be maximally different?
Like 0.4.
Okay. So what you see here is right after the 90-degree pulse, both tissues would give very little signal because if you did another pulse at this point, there'd be very little Z component of the bulk magnetization vector, so you'd have very little resonance. If you wait too long out here, both of them have recovered and they'll both give a lot of signal. So there's a sweet point in between here where you can maximally differentiate these two tissues based upon their T1 times. And then this just is another example showing these two curves. So this is the short TR range. So this is the range, and this is why Michael said that T1 weighted images use short TRs, because if we use a short TR, we can maximally separate tissues with two different T1 times. If we have a long TR, there's no separation between the two. So how do we do this? What you do it is you determine the TR. So if we give a 90-degree pulse, the spins start coming back up again. If we do the next 90-degree pulse at a time when there's a big difference between the two, the short T1 tissue will have a bright signal. The long T1 tissue will not have a bright signal. It'll be dark, and we'll be able to differentiate the two very well. If we have a long TR, like 3,000 milliseconds, both of them would have recovered, both of them would be bright, and we would not be able to distinguish these tissues very much based upon their T1 content. So the bottom line then is most of our imaging, if you have a long TR, you have poor T1 contrast. If you have a short TR, as long as it's not too short, you have a strong T1 contrast. So typically at low fields like 0.2 Tesla, you like to use TRs around 400 milliseconds to separate them. The TRs increase a little bit as you go in higher in signal intensity. So typically at 1.5 and 3 Tesla, we like to use about 600 or 700 milliseconds to separate the tissues. Now, there's another way that we can get T1 weighted images. And this is a little bit more complex sequence, which is called inversion recovery. Michael, what's inversion recovery?
Let's see if I could try to explain it. So the way I understand it is, after giving I think 180-degree pulse, you wait a time where you can get the signal, and you will null out either. You usually null out either the water or fat. That's kind of my rough understanding of the inversion recovery sequence.
Oh, okay. Well, let's just say then that we have two tissues here. One is a fat tissue, and fat has a very short T1 time, so it recovers very rapidly. And let's say we have water. Water turns out, and we'll explain why later, water has a very long T1 time, so it takes a long time to recover its Z component of the bulk magnetization vector. So let's think of this as being fat and this as being water. So with an inversion recovery, what you do is you start out not with a 90-degree pulse. You start out with a 180-degree pulse, which flips the spins 180 degrees into the negative, the bulk magnetization vector 180 degrees into the negative direction. Now, if you just stopped at that point, what happens is after the 180-degree pulse, you have no XY component, and therefore you'll have no signal. And if you just wait over time, what would happen is the XY component will stay zero, the Z component will will go up to zero, and then go all the way up to 1 and recover. And it recovers 2/3 of that distance roughly, and 1 T1 times for the tissue. And that's what this shows. So first, if we give a 180-degree pulse, we're going to get no signal. But then what we do is we wait a while. In fact, we can wait a short while until fat comes up to the 0 point. Now, when the fat comes up to the 0 point, it means that there is no Z component of the bulk magnetization vector. So if we then start a regular pulse at this time and give a 90-degree pulse at this point, fat will have no Z component of the bulk magnetization vector, so there's nothing to rotate in the XY plane, so we'll get no signal from fat. But what we have down here is water is in a negative Z component here, but if we give a 90-degree pulse, that will rotate it into the XY plane, and it will give a signal. So with uh, so if we use what's called the time between the 180-degree pulse and where we initiate the 90-degree pulse or initiate the spin echo sequence is called the TI or inversion time. If it's short, we can nullify fat, and water gives us a bright signal, and that's what's that called, Michael?
That's a stir sequence?
That's a stir sequence. Now, the other thing you can see here, if we wait a longer TI, we can come out to the point where water crosses the zero axis, and now fat's almost completely recovered. So if we have a long TI here, give a signal, we'll have bright fat, and we will nullify water. Sheila, or let me see, Yuri, what kind of sequence is that called?
Uh, it's fat. Let's see. It's a F stir.
Well,
I mean,
it's called a flare sequence, fluid
sure.
attenuation inversion recovery, and both of these were really invented by Graham Bitter when he was in England. Now he's down at UCSD. So, and we know that flare is very important in brain imaging. It really allows us to see. It was originally created in brain imaging in order to be able to see periventricular signal abnormalities. They were often kind of obscured by the very bright signal of the water in the ventricles on T2weighted images. By nullifying the water, then you're able to see the periventricular white matter changes much more prominently. Stir was initially developed to nullify fat in the subcutaneous tissues of the chest, but because with chest breathing, when people try to do chest MRI, you'd get a lot of metal, you'd get a lot of artifact from the breathing, and you'd get what looked like ring artifact going through the chest. So by nullifying the fat in this way, you could improve the images of the thoracic uh, cavity. That turned out not to be very helpful, but it turns out that that very rapidly became a useful sequence for bones and soft tissues, really looking for subtle areas of edema. And it gives kind of a combination of T1 and T2 contrast, which is, as we know, is very sensitive for pathologic conditions. So that's inversion recovery sequences. And if we can see here that actually, if we pick any time in here as our I inversion time, we can, especially actually right here, but any time in here, we can get very good separation of tissues based upon their T1 times. So we know T1 weighted images, they differentiate tissues based upon T1 a lot of times. We know it's short TR, short TE, and some gradient echoes. And we know it's very good for looking at anatomy, especially the musculoskeletal system, for blood. And T1 weighted images are very useful for a lot of IV contrast. Most of the IV contrast we use selectively shortens T1 times. And therefore, with the T1 weighted image, we can best just differentiate between tissues with normal T1 times and those tissues that have shortened T1 times because we've given contrast. And they become bright because they have short T1. And it's just an example of tumors that can be seen very nicely, separating fat with a short T1 from tumors, which is primarily water, which has a longer T1 and therefore doesn't give a very good signal. And if you look, it does change a little bit with field strength. It increases, as we said before, generally quite a bit from 0.2 Tesla to 1.5 Tesla, and about 20% from 1.5 to 3 Tesla. The amount of increase actually depends upon what kind of tissues you have, but most tissues within the musculoskeletal system, you'll get about a 20% change in T1 from 1.5 to 3 Tesla. Uh, Now, there are reasons that are relatively well understood as to why the T1 time changes depending upon the field strength. Well, let me, basically what happens is that a T1 time is another term for it in physics is called a spin lattice relaxation time. And what allows the nuclei in the z direction to go back to the baseline state. They want to go there because that's a low energy state, which we talked about before. But remember, in quantum mechanics, the nuclei can't transition from one state to another, even if it's a lower energy state, unless there is a photon of energy of the right amount to allow them to transition from one level to another level. And it turns out for in the z component of the going from one energy level to another energy level, the energy that the spins have to get to be able to make that transition comes from the vibration of the other molecules around it. And it turns out then that as you go to higher and higher frequency, this transition becomes more efficient if you're dealing with smaller molecules. Large molecules tend to vibrate and spin at low frequencies. Small molecules tend to vibrate and spin at very high frequencies. So what actually happens is, and actually this is a decrease of T1 time from 1.5 to 3 Tesla. What happens is uh, with that when you go to 3 Tesla, uh, the tissues tend to have large macromolecules, and most of the tissue there are fewer molecules of the right size to resonate to be vibrating and tumbling at the Lamar frequency, and therefore the time to recovery becomes slower. And that's why we tend to increase the TR as you go to higher field strength in order to best separate out the tissues, because the T1 times are longer at higher frequency than there are at low frequency. And the reason for that is that there are fewer molecules that rotate and vibrate at the higher Lamar frequencies. And therefore, there's less energy packets to stimulate the transition from going from the high energy state down to the low energy state to be able to recover the Z component of the bulk magnetization vector. I'm sure that's more than you wanted to know. Okay, but there are reasons for that. Now, T2 weighting uh, is any pulse sequences which primarily separates the signal intensity from tissues based upon the T2 time. And this is just an old image from the mid 1980s showing a large tumor in the posterior fossa here. And we found out very early on that T2 weighted images were very sensitive at detecting pathology. And that's one, the reason for that is that tumors are very poor in their use of water. They tend to have a lot more free water in their cells than normal tissues have. So they have a lot more bulk water. Water has a very long T2 time, and long T2 times means high signal intensity, as we'll see in a minute, compared to normal tissues. Also, edema states have a lot more free water, not inside the cells, but in the intercellular medium, and therefore they tend to also be bright on T2 weighted images. So T2 weighted images tend to be sensitive for pathology in general, which you all know. So if we go back to our old diagram here, 90-degree pulse, we rotate the bulk magnetization vector in the XY plane. It then spins around, and that spinning around then induces current in our receiver coils, as we talked about before. We know that that signal decays fairly rapidly because the spins get out of phase, and once they get out of phase, we get no signal from them. So what does this look like if we have a graph? This is right after the 90-degree pulse, and we'd have the signal being maximum because all the nuclei are forced to be in phase right after the 90-degree pulse. But after the 90-degree pulse, they rapidly start getting out of phase. If you have tissues with a short T2, they get out of phase very rapidly. Tissues with a longer T2 get out of phase much more slowly. It turns out that long T2 tissues tend to have one thing in common. They tend to have a lot of bulk-free water, just a lot of water, because water itself has a very long T2 time. Short tissues would be tissues where the water or the protons are closely associated with large macromolecules or fixed in space. Now we can sample T2 time because if we give a 90-degree pulse and then we do 180-degree pulses, a series of 180-degree pulses, what you'll find is that the signal will go up to the T2 time, and by taking several different pulses, you can then generate the decay curve here, and that can then you can then calculate what the actual T2 time is. So if you have uh, uh, images, we can have T2-weighted images where we just typically take one echo here. And if it's a long echo, we can see we can separate the tissues here. If it's too long, all the signal goes away and you just get a black image. If it's too short, both long and short T2 times will give a lot of signal and they'll both be bright. But if you wait long enough, you get a point where you still have enough signal in both of them, but you'll have a very good separation. So most tissues in the musculoskeletal system at zero point 0.2 Tesla, you tend to like to use TEs of around 100 milliseconds uh, to separate them. Uh, at 1.5, if it's a standard spin echo, you like to use around 80 to 100 milliseconds. If it's fast spin echo that we'll talk about here in another lecture, we like to shorten that down to around 70 milliseconds. If we go to 3T, it turns out we can get very good separation at lower TEs. And you also, as the lower your TE here, the higher you're up on the curve here and the better signal to noise you get. So typically in the musculoskeletal system at 3T, I like to get a T2 sequence with a TE of about 60 milliseconds. If you go longer than that, you just lose signal to noise and you don't gain any contrast. So around 60 milliseconds for a T2-weighted image at 3T. So if you remember our sequences, what we had here was a 90-degree pulse, and we got a free induction decay that dropped over a time course that we call T2 star. T2 then dropped more slowly, but if you remember, this is actually the signal in our wire. So the signal in the wire would drop very rapidly with T2 star. But if we give a 180-degree refocusing pulse at a time tau, if we wait a time 2 tau later, we'll then get an echo here, and we typically image off this echo. And the peak signal intensity on this echo will go up to the actual T2 time, to the T2 curve. So now the question is, how does this 180-degree pulse create an echo? Sean?
So after you give the 180-degree pulse, that would flip the spins from dephasing or decaying. It flips them back over so that at the T2 tau they will be the strongest in the XY direction. So basically, you just reverse the dephasing or decaying, so they go back to the same point.
Okay, so let me explain a little bit differently, and we can use this curve here. Right after the 90-degree pulse, all of the nuclei are pointing in the same direction, and they're spinning around in the XY plane together, and we call that in phase. We know that they're all at slightly different magnetic fields, and therefore they're actually going to precess at slightly different frequencies, and therefore they're going to rapidly disperse and get out of phase. So if we wait a while, they'll be out of phase. But now we can do a trick. Notice that as they go around here, there are fast guys that get out in front. There are slow guys that are back here behind, right? Now, if we give a 180-degree pulse, we're going to flip everything over here. They're still precessing in this direction. But after the 180-degree pulse, notice something here, that the fast guy, the guy that's in a higher magnetic field, is now behind. Yeah. And the guy in the low magnetic field who is precessing slowly is now ahead. And if you wait a time tau later, the fast guys will catch up, the slow guys will fall back, and they'll come back in phase again. It's like, let's talk about a race here. And we've got a tortoise, which is slow, bicycle, a race car, an airplane, and a rocket. So they first all start out at the same point. Say they're starting out here in Los Angeles. You shoot the gun. The tortoise moves down to the end of the hall. The bicycle goes from Santa Monica or from Los Angeles to Santa Monica. The race car will drive off into the ocean, but will stop right before it gets to the ocean. We have an airplane that'll fly out over the ocean and a rocket that'll make it to Hawaii. At that point, we say, everybody turn around and go back toward the starting point at the same speed that they were going before. What happens then, if you do that, they turn around and go back, and if they go back at the same speed, they'll all reach the finish line at exactly the same time. Any questions about that? So what we have then, just like this, we have some spins that are slow, we have some that are intermediate, and some that are very fast. But when we give the 180-degree pulse, what we're doing is telling them all to turn around, and now the fast guys will catch up the slow guys to the slow guys will fall back to the fast guys, and at time 2 tau, they'll all be back in phase and we'll get a signal. Any questions? Okay. Now, Sheila, will that signal be as strong as it was right after the 90-degree pulse? No. Okay. Why isn't it as strong as after the 90-degree pulse when they're all back in phase again?
Because I think that it's because of the free induction. Is it the decay? I think now it's already decayed.
Well,
And it looks
okay,
like
so why is
you'd need another
this
pulse.
one drops all the way down to 0.
Mm-hmm.
But then when we do our echo, it just comes up to here. Why doesn't it come all the way up to the top?
Because the pulse? No.
There are two things that are causing the spins to get out of phase. Now, the one thing that has to occur for this experiment to work is that the tortoise has to have the same speed, the bicycle has to have the same speed, the race car, the plane, and the rocket all have to be traveling at the same speed going out and coming back again. So if you have any spins that are in different magnetic fields, as long as that magnetic field stays the same, the 180-degree pulse will exactly cause it to rephase and come back and give a signal. Okay? So what might cause us to lose signal in this process? Michael?
I think that you lose signal anytime. You have maximal signal just after your 90-degree pulse, and then anytime after that, you start to lose signals.
But remember, if the fast guy stays fast, the slow guy stays slow throughout the whole process, then they'll come back and exactly be in phase, and we'll get the full signal. So what's happening here is that the very rapid T2 decline here is due to two factors. One, the bulk of this is the fact that the nuclei are fixed in different fields, strengths. And then when and they get out of phase very rapidly. But if they stay in the same magnetic field strength the entire time, when you give the 180-degree pulse, you'll get complete rephasing and you'll have the complete signal coming back. So that means there's a second component that's causing these to get out of phase, and that's a component that's this would be time independent. This is one that's time dependent, and that is if there's any process which is occurring so that a given nuclei may be slow over here, but then it moves around and becomes fast at another time. And therefore, if for instance, this tortoise stays slow, but if he hitches a ride on a bicycle on his way back, he's going to come past the finish line. If 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 going out, the guy in the bicycle hitches a ride in a car, he's going to speed way out and be way out here. And then if the car dumps him off and he's got a bike back, he won't make it back to the finish line in time. So if the magnetic field inhomogeneities are fixed in time, you'll get complete rephasing. But the problem is that a lot of the variation in the magnetic field strength in an exact location of where a nucleus is located varies with time. And a lot of that variation has to do with the fact that the nuclei themselves are magnet. They interact with each other, and that interaction changes over time. So so some of these nuclei will have their precession changed because their frequencies will vary over time during this experiment. And that's called a time-dependent dephasing, and that can't be corrected by a 180-degree pulse. Okay, so why don't we stop here, and we'll come back to this next time, and we'll talk about why this is important when we're trying to sample tissues. Okay, any questions? All right, I'll see everybody tomorrow.
Thank you.
Thanks.
Thanks very much.
Yep.
Okay, thank you.